Hello, my fabulous chemistry students. Unit 8, Video 7. We got one more after this. Today we deal with entropy. Entropy is the amount of disorder in a system. And as chemists, we're interested, can we actually define it? Well, believe it or not, we can. We, the universe and nature itself wants disorder because to order things takes energy. So I always want to be at the most stable, lowest energy state, and that is actually disorder. And if you need some, what I would say, reinforcement on that, is look around your room. How much energy does it take for you to keep that thing organized and ordered? Quite a bit. Okay, if you're anything like my kids. So entropy is the degree of randomness or chaos or disorder, the messiness in a system, if you will. Okay. So the greater that is, the greater the entropy. Okay. The more order you have, the less entropy you have. The less order you have, the more entropy you have. Okay. So order and entropy, I can kind of um, flip-flop those terms, if you will. But this is a concept that we have to get down. The physical state of the matter has the highest entropy. Well, that would be gas. That would be the state of matter where the molecules get to move around the most and have more randomness to them. Randomness and disorder are two other words that are very closely linked. All right, now, the most ordered of all the phases, very rigid, would be solid. Okay, liquid becomes more ordered. I'm sorry, more disordered because the particles are allowed to move around. So as I get the liquid pieces, they're allowed to tumble all over each other. Okay, remember we draw it to the sides of our container. But now aqueous is a little bit different. Now aqueous, of course, is liquid, but it is now in water. So now I have all of these pieces that were in my other liquid interdispersed with all these water molecules. So now I have water and the liquid. So that's what makes it a little bit more random than just pure liquid, because there's in pure liquid, everything next to each other is its neighbor, the same thing. Now gas, on the other hand, gas, remember when we draw gas, we're going to start with one on each side and then completely random. That randomness leads to this disorder thought. Okay, so gases have the most randomness or the most disorder. So that's really all we have to do with these games is, figure out what kind of phase I'm in. So the draw of the particle diagrams, I did really just kind of start this, but let me just redo it. Solid, remember, we're pretty ordered and rigid, not touching the walls. Okay. Liquid, I want to be touching the walls. Feel the shape of my container, but I don't take the volume of my container. And these things can all roll around each other, so they can change their neighboring molecule, but their neighboring molecule is always going to be one of itself. Now, aqueous is where I'm in water, and I have my solute, but that solute is dissolved or mixed with the water. So now, every solute molecule doesn't necessarily have another solute molecule next to it. It could have a water molecule next to it. So that leads to more disorder. Gas, remember again, I just did it on the other page. I'll do it again real quick. One on each side and then completely random. No pattern or pattern to it. Okay, more random. So entropy increases when a compound is broken down. It decreases when a compound is created or formed. So you can think of, it's a lot more ordered and structured when I make bonds. So these are the two things that I'm going to use to decide whether or not a chemical reaction is increasing in entropy or decreasing. I'm going to use first the states of matter. Solid to gas is increasing, my delta S. And then this statement here for when I'm not changing phase, I'll go by the compounds being make or broken. So those are my two basically rules or steps, okay? So let me do a few of these and then you're going to do the rest for practice. Let me start with number one. I'm going from a solid to two different things, first of all, which is a breakdown. So that fits into my my increases. And then I also have a solid and a gas. So I am going from solid to a gas that I'm increasing my entropy. So I'm increasing delta S. Okay? Number two, I am at a liquid and I'm going to a solid. So if I am at liquid and I'm going to solid, that's backwards, I am decreasing my delta S. I am becoming more ordered, so my S goes down. It's almost an inverse relationship. Okay? Three, another good example. Three, I am all gas. So my phase change does not help me in this case. So now it's just, am I breaking down or building? So I have two different things, more random than one thing. One thing is more ordered. Okay, I am creating bonds when I make NH3, so my delta S is decreasing. Okay, you guys getting the hang of this? It's really pretty much that simple. As you continue to do this, remember on the note on the bottom, if all states are the same in the reaction, count up the number of molecules on each side. The rule is more to less molecules is a decrease in delta S, less to more molecules is an increase in delta S. So that's your little rule of thumb when they are all in the same state. Okay, so you guys get to finish those as your practice because there is no practice packet. Be sure to finish them to get full credit for your homework today, please. And now understand that entropy, without the T, or I'm sorry, without the H, entropy is delta S, and it's the amount of randomness or disorder in a system. Best of luck to your studies and see you tomorrow in school.